Started here this morning. Um, First, I wanted to thank all of you for attending our Tech Tuesday session. For those of you that have attended these in the past, we have done a Tech Tuesday probably for about 15 weeks or so, and we had covered a wide range of topics from applications to controllers to PID fundamentals, and we're starting our new session here with Tech Tuesdays with Honeywell HTS Richard Reyes today, special guest for us. These sessions will be recorded and put on our YouTube page for later viewing. So feel free to visit our YouTube page and take a look at our Tech Tuesdays. Richard comes to us from Honeywell HTS this morning. Richard is currently the oil and gas market lead for Honeywell Thermal Solutions and has over 30 years of experience in fired combustion systems and applications. He is a registered professional engineer and holds an MBA from Baldwin Wallace. And he is a two-time Honeywell President's Club winner, which that's a pretty prestigious award, Richard. I was on one of those, and I can say that you're amongst some top people within your group when you go to those. So congratulations on that. Also an Innovation Award winner from BOC Gases, now Linde. Today we're going to go over some Honeywell combustion and also safety shutoff valves. We're going to talk about flame failure response time and some other things surrounding the combustion world. And if we have any questions at the end, we can go ahead and either type in your message or we'll leave a session for you to speak up and have some questions at the end. So with that, I will turn it over to Richard and we'll proceed forward. Thanks, Richard.
Yeah, good morning, everybody. Thanks for the intro, Jeff. And with that, just a quick check, so the audio is good. So I'm going to try to roll through this. It's kind of an interesting subject that we're going to cover. We're going to hit on some interesting points on, safety instrumented functions, critical items that should be considered and thought about. But before I jump into that, I just wanted to kind of ground, who we are from Honeywell Thermal Solutions. So we are basically part of the HPS group, and Honeywell Thermal Solutions is of several companies, like Hauck, Eclipse, Maxon, and so on. And the way we look at the portfolios is we actually deal with burner management systems, fuel delivery, of which we're going to talk about the S8000 today. We also have thermal transfer. We have about 100 different burners. I still am confused on how to apply all of them. And then we have, complete solutions. We do audits, we do complete systems, and in the audits, for example, we try to make sure things are compliant to the prescriptive standards. I did mention about the flame scanning here real quick. We'll touch on that a little bit and how that affects safety instrumented functions. But just wanted to give a quick idea in the buckets of expertise that we actually deal with. Everybody probably is familiar with the fired system. Just to kind of ground that, we've got a process that has heat transfer, whether by convection, conduction, radiation. We've picked the right burner for that. And then to support the combustion and heat delivery to the process, obviously we have to control fuel and air. There are applications that are natural draft, but registers and primary, secondary air that we deal with as well. Got emissions, tie all that together to optimize what you're doing. In order to get there, I'd like to touch on how we look at things. Every process is slightly different. I deal a lot with the oil and gas and petrochemical industries, so we would probably look at a crude oil heater, but we do deal with 28 other verticals, whether it's a bakery oven, a dryer, and so on. But the point is, you want to apply a particular burner to the particular heater that's involved. So if you had a crude oil heater, you would probably use a natural draft burner, and then your burner management system would probably be a PLC base, so you can manage availability and safety for your specific process. But we also deal with simpler systems that actually can benefit from what we call fixed proven logic. So like our 7800, we have Slate, which is a configurable fixed logic that we can put together. And then there's also other devices that do the same. And then we can talk about, how do you control, air and fuel. We have high precision actuators that we can apply for efficiency and so on with Modbus communication to see where the valve actually is in position. And then lower torque actuators, nothing different between the two in terms of what they do, but in terms of performance, there is a difference. Then on the shutdown, which we're going to talk about today, you can kind of see here we have the S8000, and you can see all the different performance criteria that can be met. Each one of these could take 15-20 minutes to talk about, but there's also other valves, shutoff valves that have listings and would probably be applied maybe in a bakery oven, but in a refinery petrochemical, you're going to have to take a look at other standards. So we can take all this and put a system together. This is what the portfolio looks like that I deal with. We do, fuel trains and so on, NFP85, power piping, B31.3, and we package different burners and systems together. And then here you see the S8000 with a panel here. We do valve diagnostics, so we can actually monitor the health of the valve. And then industrial flame monitoring, where we can actually do high discrimination in terms of what the flames are doing and change thresholds and do some detailed tuning, as compared to say 7800 that says, hey, you have flame or you don't at a set threshold. Other performance standards that you may or may not be familiar with, fire safe, we'll touch on that. And I talked about the high precision actuator and then burner management systems. So that was kind of a quick overview of what I get involved with. So what we're going to talk about today is the whole issue of a safety instrumented function. When you read several different standards, NFP 85, 86, 87, or look on API 556, or I sit on API 535, where they're talking about burner testing, and you now can buy an API 535 burner. There's also API 565, for example, that's being developed because some processes you can't quite apply NFP 85 to it because of the way the system runs. However, what's important is the whole idea of how long does this safety instrumented function take to respond to bring you to a safe state, which means to shut down fuel flow to your fired asset. I will say that there's also a issue with the basic process control system, which tries to keep the system within limits in terms of temperature. But usually when something is already gone bad, it's already happening way before. Going fuel rich, the flame goes out. Only then does the sensor pick up that and then actually get a signal to the safety PLC to shut down. So one of the things that we're going to talk about is flame failure response time. The API 556 or it's several of the other standards will tell you that you have 0 to 4 seconds. You have to comply with that. And then some standards, like in CSA, they may say the overall system should not exceed 3 seconds of total time to shut down. So you'll see all of a sudden, if I were to dial in 3 seconds here, I can't really comply because I already used up the total time if you're looking at a CSA standard, for example. So safety response time is important. We have talked to several companies that have used what they call low NOx burners over several years. And what they've found out is they're having more frequent flameouts. Low NOx burners are finicky, and by default, those frequent flameouts actually put a demand on this system. And what they have found out is some groups have determined the amount of time it takes to shut this down affects the overall severity of an event if it were to happen. So keep that in mind. So how does this look like physically? So if we look at the sensor world, could be a pressure transmitter. Showing here the configurable industrial flame monitoring, where we can actually monitor UV independently, IR independently, and then monitor the cumulative signal, which becomes part of the digital safety signal loop with a voting architecture to say, hey, I have a safety PLC that says I've got 3 scanners, 2 of them saying everything is okay. Let's keep running and take care of that one, make sure what's wrong with it, fix it. Or if 2 of them say the flame's gone, we're probably going to shut down. That's what they call a 2 out of 2 voting. Goes through the safety PLC, and this is the S8000 valve. Like I said, we're going to deep dive a little bit more on that to shut the fuel flow off to the system. Here is an example, some more details in an actual NFP 85 application where they're actually applying ISA 84, which is similar to IEC 61508 in terms of saying, hey, arrange the fuel train this way per NFP 85, and then from a seal and safety standpoint, how good the equipment needs to be to say, hey, we're going to mimic SIL 2. If you take a close look here, you're going to see a device piggybacked on here. This is called a manual reset. And I want to mention this early because I'm going to touch on that again, because the performance standards and the prescriptive standards actually talk about this, but yet many don't take into account of applying this extra level of safety in their shutdown system. So what happens typically in applications, you'd have an operator. What we have seen is you'd have an operator sitting in a station, not to overwhelm the operator. They don't get to see all the data behind the scenes. This is an example of an actual signal that's taking place. And the red line here is infrared. The dark line here is UV. And in this particular process, when they put steam to quench the refractory, if you're familiar what steam does, steam actually completely masks the UV signal. So if you were monitoring this, you would actually see what actually took place. The signal dropped, the overall signal dropped, and you would see that the UV was the factor. But typically what they'll have in the control room, they'll actually have the fired asset depicted, and you'll actually have a flame on or flame off indication. And typically what would happen is if they were to lose one of the scanners, they get, a flame off indication, either get an alarm, they check it. They will call an I&E person to go out and physically take a look at, the device, see what's wrong with it, are the cables connected, or make some tuning changes. If you're bringing back an analog signal, you could see that you still have a live signal, but often than not, all they're seeing is on and off. But there may be a live signal. So anyway, they can go back and make those tuning changes. So to kind of talk a little bit more about how process affects safety and reliability, trying to balance the two things. I'd like to use the example of a sulfur recovery operation, which is kind of interesting. You have to have this if you're in a refinery in order to take all the sulfur that's been taken out of the crude that comes off the amine plants, and then that H2S gas shot to this reaction furnace, and they actually recover sulfur through a catalyst, and then they do heat recovery. So there's a lot of stuff going on. This unit actually is fired at first, with fuel gas and get up to a certain temperature, and then they transition into the H2S feed. So this creates all sorts of interesting things. For me, this is probably one of the more complex fired systems I've ever dealt with over all my years, except maybe a corner-fired multi-level boiler. And here's what can happen to you. I'm showing this to give you an example of, a lot of people look at flame signals and they're trying to understand what's happening. If it's a real simple fired single burner, natural gas fired system, not a lot of variability, pretty steady state, you're not going to see variations like this. So on this reaction furnace, you see a burner here. If you're familiar with these burners, there's a lot of stuff going on. There's oxygen coming in, there's H2S coming, there's fuel gas coming in, sour water gas, and even recycled gas in this particular burner. So you can see what I want to point out here. You'll see this red line here is the infrared signal, and you can see it moves around quite a bit depending on what's going on with the process variables. This data actually came off an actual end user. They allow me to use this as long as I took the ledgers off, but I will tell you that this here is H2S, this is sour water gas, and then there's also oxygen going into the system. But here we see a big dip in the signal, because this green line, remember I talked about a cumulative safety signal. You could see it here. If you walk the process backwards, it'll recover. But as you're going from left to right during normal operation, you can see that this signal actually drops pretty low. So if you had a typical flame detection system and the threshold would say here, you would actually have a trip and lose this fired asset and have a shutdown, even though you still have signals going on. So if you're pulling back signals on an analog basis and you're able to see them, you could see what's going on here. So we can tune these thresholds. So just trying to point out that you can have a real complex scenario depending on the process variables and what your signals are, but all this stuff is fully tunable. I do want to mention that even all these tuning variables can be looked at like this. We can change the flame on set point, flame off set point, and then in this particular case, we could say, hey, the flame is on, and then we can see the contributions of infrared, solid state UV. That's a whole different discussion on what that's within the visible spectrum with IR, and then what the contribution for the UV is. And we actually can make this data mobile. This is per our thermal IQ technology. That's a whole other discussion that can be had on how that actually gets done, but I thought I'd point out that we can actually make this data mobile. So how do we deal with tuning these devices, kind of trying to set up the whole idea about flame failure response time and just trying to emphasize how complex some processes can get. So here's an example of what we call a process walk based on that reaction furnace. We would track all the process phases, monitor the signal strength to try to figure out how we would want to tune this. And what we're looking for is the lowest and weakest signal that we get. And we actually tune for that. We manipulate shutdown criteria because what we would do in this particular process, when we're on fuel gas, we would actually trip the unit and make sure that the flame failure response time, which means the shutdown, that it sees it happening, is less than 4 seconds per all the prescriptive standards as a requirement. Adjustments on devices that we deal with, like these industrial flame monitoring, only allows you to adjust to 3 seconds, even though you can have 4 seconds per standard. So we want to make sure that happens in order to optimize the tune on this side, because this particular process, as it ramps up in temperature 1800 plus, it goes into a process fired condition, which have to have different considerations, pretty much dominant on the infrared signal. So once again, flame failure response time has to do with, did I see a flame within 4 seconds? So if you have a very unstable fire process like you saw earlier in the prior slide, you may have to dial in a flame failure response time probably of 3 seconds in order to avoid what they call nuisance shutdowns. There's also a concept called the flame on delay, which can also cause some issues on flame out. So if you were to say, I want to put my flame failure response time to 0, which is actually 250 milliseconds, and I put on my flame failure response to 0 seconds and my flame on delay at 0, what you're actually doing is you're saying, I want to instantly confirm that there's a flame, and then I want to see that within 3 seconds. If you think about that, if the flame momentarily moves out of the line of sight, you actually are going to lose the flame if you had the flame failure response time at 3 seconds. Conversely, if you put 3 seconds for the flame on delay, you're asking the device to wait to look at the flame for 3 seconds before you confirm you have flame. So if you were to tune 3 seconds for flame failure response time and 0 seconds for the flame on delay, that is your best scenario to deal with nuisance shutdowns, because what you're saying is, I'm going to give it 3 seconds to see a flame, and then I want to, as soon as I see the flame within that 250 milliseconds, I'm going to confirm it's in there. So that's how we manage unstable flames to keep you out of a scenario from having to do what they call frequent relights. Frequent relights causes dangerous issues, because now you're putting demand to relight on the shutdown system. If something goes wrong, I've seen that happen in the past where frequent relights ended up blowing up a scrubber, for example. So here's a tuning map that we actually deploy, when you get into functional safety and MOC, management of change, which you deal with in a lot of petrochemical and refineries. Surprisingly enough, a lot of people are not, disciplined enough to collect the data. But if you tuned like this reaction furnace that you can see here, where there's 3 scanners that are using the 2 out of 3 vote, we had to dial in, and the point here is we had to dial in 3 seconds in the flame filter response time and the flame on delay at 0 to minimize the what they call a nuisance shutdown. Works very, very well. If you put 0 here and put 3 here, I will guarantee you on this particular process, you will be calling me and I will ask you to send me your tuning map, and the first thing I'm going to change is these 2 variables. But the big point here is now we've taken care of the reliability and safety part and balancing the 2 things from frequent relights. I now added 3 seconds. This is the whole point of this part of this discussion. I have to do that in order to avoid what we just talked about. That comes into play. Once again, I'm showing this safety instrument and function. So if you had a boiler, you can have several, right? Feed water level, steam pressure, steam temperature, low gas pressure, high gas pressure, and then obviously the scanner is probably the catch-all, because I sometimes tell people if you had a slug of inert gas going through for about 3 seconds, pressure switch is not going to catch it. The only thing that's going to catch it is the scanner. So a lot of initiating causes that get reported kind of go like this. They'll say, hey, we lost the flame. The scanner detected that, and it asked the safety system to make a decision to shut down, and then the final element needs to close. So that's coming back to that to now talk about what's important. So we talked about 3 seconds. In some cases, there's 3 seconds that's permissible. Obviously, the shutoff valve has to be the area you're going to have to look at to close as fast as you can to minimize the overall time. So let's touch on the S8000, and just to kind of give you an idea that differences. There are ball valves out there which kind of do the same idea, same function, but the S8000 valve is actually a fast-acting linear valve. It actually closes in the vertical direction. A lot of people think it actually closes vertically down, but it actually closes vertically up. Metal to metal seats, nothing to adjust. We do test the FCI 70-2. Some people are familiar with API 598. The interesting part of 598 is they actually have in their table 0 leakage for valves that are 2.5 inches or smaller, but there's an asterisk next to the 0, and they actually say in the clarification that they mean less than 1 bubble per minute. So if you look at FCI 70-2, to which we test our valves to, we actually do 0.3, 0.2, 0.1 bubbles per minute on 8-inch valves, for example, which is actually less than the 1 bubbles per minute. And then if you look at the larger sizes of valves compared to FCI 70-2 versus API 598, FCI is actually stricter. So it's good to kind of, when you look at the comparison of the leakage rates for Class 6 metal seats for a valve that has no adjustments required. So basically this valve has no maintenance that you can do because it actually wears in, not out on the sealing mechanisms on the wetted parts here. This is the actuator on here, and this is what the valve looks like. There's some other things, wear in, not out. Some valves to get a Class 6 have to use soft seats. I don't like to do too many comparisons, but these do require adjustments and they do wear out. So now to the combustion safety aspect, like I said, of what happens in terms of overall time and severity, in terms of why is it essential to have a valve that closes less than 1 second. I did a calculation that if you took a 4-inch valve that is flowing gas at 20 psi with a 4-second delay to shut that down, if my math's right, I double check myself that the total energy that flows to the fired space is something like in the order of 100 sticks of dynamite. If that doesn't catch your attention, that every second matters, it does to me. And as it's been explained to me, that the severity of events has to do with this amount of time that it takes. So just looking at agency standards and so on is not enough, right? Because there are valves out there that actually take 1 to 1.5 seconds per inch diameter to close. So I frequently hear upgrades that some people are doing, that they're actually trying to take out valves that they know close less than more than 4 seconds, and they're looking at reading NFP 85 and seeing that it says, wow, you need to have a valve in there that closes less than 1 second, and we have that discussion. So how do these valves get into a plant that closes 4 seconds or more? So this is just a summary of NFPA and API and different things, just trying to point out a few things that if you're writing a spec, how do you look at that? So if you look at the agency listings, FM, for combustion service, gas service valves, UL 429 or CSA in Canada or the European EN 161, you'll see that we submit our valve for fit and function per the design, and the agencies would actually test the valve. For example, to get an FM listing, they'll cycle a valve at 10,000 cycles at max temperature, and at min temperature 10,000, and they have an allowable leakage limit for a particular size valve. I think this is for a 3-inch valve. And then UL has, they go more cycles, 50,000 on high and low. And then CSA pays more attention on the high end and also on the low temperature, and they have the leakage rates fairly similar to the UL. And then EN is stricter. We test the FCI 70-2 in this particular size valve, and the permissible limit per FCI would be 0.15 cubic centimeters per minute. Then I jump over here, the prescriptive standards NFP 85. So if you have a boiler and if you have authority having jurisdiction, however you're doing stuff, whoever comes in and checks your boiler, they're going to want to make sure that, hey, what's the valve that you have on there? They may actually look at what agency listings that you have on there, because if you have an FM valve, FM allows up to 5 seconds for a closing speed. So when I look at specs that say, okay, I need a valve, I typically would find just FM listed, but no one actually puts the detail on the speed of closure. So if you're doing a boiler, you can see it's a little bit conflictive. So just having a listed valve is not enough. You have to take a look at the, does it have EN 161 or UL? But if you're not sure, you may even have to go as far as doing what I call third-party verification and verification that, yeah, the valve does indeed close less than 1 second. So also, you may be self-insured. If you are insured, you obviously can have to declare and follow the standards in order to make sure you have your insurance. But if you're self-insured, more often than not, I kind of find a lot of people are still using API 556, and the closure speeds permissible are less than 3 seconds for a valve less than 4 inches, and from 6-inch to 8-inch, less than 4 seconds. So I've had discussions where we went and took a look at what they were following, and I said, hey, you really need to think about the closing speed and severity, especially on the boilers. And more often than not, the self-insured folks actually have this baked into their own standards. So they may end up with a valve that closes in that flavor of 4 seconds to completely close, with the ramifications that we discussed on severity. So agency listings is not enough. You have to take a closer look at what you're doing and what standards you're following. I just wanted to point out some additional information when we talked about boilers. So NFP 85 talks typically about 12.5 million BTUs and up. CSD1 talks about the smaller boilers, but what you'll see called out here in this particular range, 5 to 12.5, the 4 seconds still apply for flame filter response time. Speed of closure for the safety shut-off valve, 1 second or less. Between 2.5 and 5, same 4 and 1 second. And then what's interesting is on 400,000 and 2.5 million, they actually allow 5 seconds. If I were on this committee, I would not allow this to happen, because accumulation of gases into the fired space is a function of time. So you really should always think about speed of closure, once again about severity. And early on, I mentioned about manual reset. So even in these prescriptive standards, and I think a lot of people miss this, it says safety controls that can electronically reset without local manual intervention, such as when power or control input to the device is interrupted and then restored shall not be permitted. Kind of an interesting thing when you think about it. You could ignore it, but then again, if you look at the performance standards like IEC 61508, it actually states something like this: no one can inadvertently allow gas flow to a furnace or heater without the burner management system being in control. It's kind of how they capture it, and that's when they get into the discussion of manual latching reset mechanisms, of which I'm going to explain how that works. Before I do that, we've had third-party verification at a different site where the functional safety corporate person actually, we had our valve independently taken to a third party, and they wanted to make sure that the valve actually closes in the time required, less than 1 second, or as fast as possible. So we actually had valves tested 0.3 seconds in speed of closure, utilizing their external solenoid mechanism. Some people like to install for reliability. They actually put solenoids in parallel, which typically you would say, wow, if you put two solenoids in parallel to shut a pneumatic valve down, if one fails open, you'll never close the valve. Fortunately, they do diagnostics on those solenoids to make sure that they are functioning correctly. And if they find one of them that actually is failed open when they're doing the diagnostics, they will go and shut that one system down, or at least know that they are aware that they have an issue and to plan for manually shutting that down or getting that out and serviced as soon as possible when possible. So speed of closure gets verified. So I actually asked the question to the customer in this case. He said, well, is 0.3 seconds fast enough? He says, I would like it to be faster, but 0.3 seconds is good enough. And then we talked a little bit about valve diagnostics, and I thought I mentioned this while I remember this. When you install a system and you install it, set it, forget it, and time goes by, does the valve still close in the time like you can see here at 0.3 seconds? Is that still the case in 6 months, in a year? Nobody really checks that. So I talked about valve diagnostics and saying like partial stroke testing. You say, hey, and they say, oh, we don't do valve partial stroke testing. I said, if you don't, one of the things you should consider doing is when you de-energize, when you're going to shut down, so you de-energize the solenoid, use that information as a DI to start a timer on your burner management system, and then to also monitor the valve close switch to make sure it is made in order to say, hey, I de-energized, I saw the VCS, the valve close switch made. How much time did that actually take? So you can kind of do some diagnostics without putting a fancy partial stroke testing and doing that with your valve to get the time, because if it never makes the VCS, you don't have a restart permissive anyway, but you still want to see what the health of the valve is, because if it's taking more than 1 second, something is going wrong with the valve. Something's happening with it, either build up, especially on valves that have been open for extended periods of time. So here's the 0.3 seconds. You can go to 0.6. When you actually, put a valve, install it, torque the valve down, and actually have gas flow, pressure to it, this time actually goes up slightly. It may go to 0.5 seconds, and that's why one particular end user actually does that. I want to touch on the ability to do external solenoids. This is or internal on the actuator of our valve. So if we take the actuator cover off, this is what they call a quick exhaust block. The solenoid assemblies here, I actually have the part of the solenoid taken off to point out this is what they call a solenoid disable knob, which a lot of people are not aware of. What this allows you is in cases where you have 120 volts, for example, if that's how the solenoid was specified, you don't have to power that. You don't have to worry about getting shocked. You can actually do this disable knob and actually put instrument ear. You can open and close the valve with instrument ear to check if the valve is functioning and running smoothly. And then you can actually determine if there's a valve with chatter. You can see whether or not it's the solenoid that's doing it. This quick exhaust block is the secret to the valve. What it does is when it senses a differential pressure, when the solenoid shuts down, it actually senses differential pressure and actually dumps all of the air that's in the cylinder out, and that's how we achieve the speed of closure, for example, like that 0.3 seconds, less than 1 second, obviously. We do have an option where, some customers want to use their external solenoid, and we can do that. This version does not have the quick exhaust block. Therefore, you will not get a listed valve in this case, even though the design is the same, because we can't guarantee less than a 1 second closure. So what we also do is we actually do a Z option, which is the quick exhaust block, doesn't have a solenoid on it. And this is a Z option, quick exhaust block. So you can use external solenoids in order to actually shut down and make sure you could shut down less than 1 second. We do have a CSA listing. We're working in the FM, but it's the same block. And that's why someone actually do a third-party verification just to double check. Yeah, the valve does close less than 1 second. And this is a close-up of the solenoid disable knob. So it gives you a couple options of what you can and cannot do. Valve diagnostics. So I mentioned valve being open for extended period of time. But do you know if it's available to shut down? You don't know until you de-energize, and hopefully it does close completely within the time frame. I did publish a thing called Don't Operate Unaware in Today's Boiler a couple of years ago. And what I did was I was comparing performance standard and prescriptive standards. Those of you that are familiar with functional safety, there's things like hardware fault tolerances and so on, depending on what they call safe failure fraction, right? So that's, all the failures minus the dangerous undetected divided by total failures gives you a safe failure fraction. Obviously, if that's less than 60%, which is very possible with a shut-off valve of this design, or a ball valve for that matter, that all of a sudden, if you need a SIL 3 performance, it may suggest that you need triple redundancy on your shutdown. And then if you look at valve diagnostics, if you have valve diagnostics, it'll actually move your hardware fault tolerance to 2. So you can get away with 2 valves. Anyway, like I said, that's a whole different subject to discuss and how things get affected. How do we do our valve diagnostics? So it's not on board a valve. We actually have a safety, we can have a SIL 2 version panel or a general purpose panel. And what it does is it has a fast scanning PLC that does a logic to the solenoid. So it'll go and say, hey, wake up the panel, exercise the following logic. Very, very simple. It's N plus 10 milliseconds. So it'll go, all right, let's de-energize for 10 milliseconds and have an interval maybe of 20 milliseconds. So we energize, re-energize. So we'll go 10, 11, 12, 13, 14, 15 milliseconds, and eventually what's actually happening as we drop the pressure in the cylinder and as we have an interval, we get a slight recovery. So we actually get to move the actual wetted parts of the disc in the seat, so it actually moves. And every subsequent pulse, it may be on the 4th one where we actually travel the disc enough where the valve open switch actually changes state. We take that valve open switch signal, which means now 0 volts, back to the PLC to say, hey, stop exercising that logic, and tell me how long it took when I de-energize to see the valve open switch change state. And that's in milliseconds. And typically, when the valves are new, it's like 12, 15 milliseconds. And so obviously if the valve is actually degrading, that time starts to go up, and we can actually set marginal alarms in there to say, hey, we have valve with tag number 707 is actually trending in the wrong direction. So, mark it for maintenance. And if the valve actually never changes the VOS state, we actually would send a hard alarm because the valve's actually stuck open. And if we saw the VCI, same thing, but run a hard alarm on there. So there's valve diagnostics for you. You can always do what I mentioned earlier. You can actually say, hey, let me time when I de-energize and when I see the VCS get made, and time that without having to do the part. It's better than 0. Anyway, so this is what they call valve diagnostics. We can do more than 1 valve. We can do up to 24, but typically it's a double block on the pilot, double block on the main, depending on what configuration on the fuel trains you're applying. I do want to talk about fire safe. Fire safe, fugitive emissions kind of probably get captured in the same goal. API 6FA and API 607 are identical. So the performance standard actually says all file elements must survive a catastrophic event, like being exposed to a fire, and be able to close and make sure to keep the gas flow going from going to the fired space. So that's why in a lot of you wouldn't see a fire safe rating on an aluminum bodied valve, obviously, right? So it'd probably be more stainless steel, cast iron, or carbon steel bodied valves that would make a fire safe rating. But I want to point out that 607 and 6FA are, when you read the testing procedures, they're exactly identical. And what's interesting is there's a burn time of 30 minutes where they actually hold the valve. This is an actual testing scenario to say, hey, what is the leakage across the sealing mechanism, the wetted parts, and then what is the leakage rate going up to the stem? So we use redundant graphite malleable seals to make sure that we meet the requirements for API. So I just wanted to touch on that we've got a fire safe rating, and it's the same as 607. So to me, this is a performance rating that kind of doesn't get credit, but it's huge, right? Because if you have a furnace that's on fire, you want to make sure, because there's secondary explosions that can happen if gases get unabated, making it into the furnace. A manual reset that I mentioned earlier, worth talking about. So how that's done is when we take the IC description of what they're asking for the latching mechanisms and so on. So what has happened is people were able to say, okay, I had a system that shut down and I had the ability to reset in the control room without even going out and taking a look. As long as the VCS was made, I have a start permissive. You know, all the shutoff valves are confirmed in the closed position. The question is, are the valves really truly closed? And there's a thing called a dangerous undetected failure, just like it's a dangerous undetected failure, where it has happened where the valve close switch, for some reason or other, got welded closed, remained that way, and the valve actually was open or partially open or fully open, and there was gas flow unabated to the fired space. So if you had that scenario and you went to reset, restart without going out and physically checking the valve to see indeed everything's actually closed position before you even attempt to restart, they have restarted and relit and launched the furnace with bad consequences. And that has happened many times. So therefore, they've come up with this manual reset to force you to go out in the field to make sure that the valve indeed is in the condition to be energized and be utilized safely. How does that work? So I kind of have a close-up here. In the true sense of the description of how this works, we actually use a Versa pneumatic block here. So let's say we de-energize. This valve actually supposed to have closed, and we want to restart. The way this arrangement is, you can energize this solenoid, and the way this pneumatic logic is, instrument air will not make it through and get into the valve, the way this is designed on a pneumatic logic. In order to put this valve in a condition to be energized, you physically have to walk out to the valve, take a look at it. Take a look and see whether it's in the closed position, number one. Number two, when I pull this knob out, I'm going to arm this valve to be energized. When I pull this knob out, what's going to happen is I'm going to let pilot air make its way through here and into the internal solenoid. When I do that, if the valve actually changes state and opens, we know that we have a bad solenoid in the valve that has failed open. And that's the only way to find out. If the valve stays closed, you're good to proceed, put the latching mechanism in, and we have instrument air safely to the valve. And then now the burner management system can, you can report back and say, hey, we're ready to start. We just armed the valve in a manual reset in a true sense. And the burner management system now energizes the two solenoids, and two solenoids. What happens here with this one, this solenoid now opens, and this instrument air passageway hits this has a piston that's designed with a certain area in order to push the shaft out and release the pin and recess. And now you have 2 solenoids to shut you down in a 1 out of 2 arrangement for the highest safety reliability for shutdown. So this is the manual reset. The other thing that's interesting is, remember, the burner management has to be in control. Conversely, if you were to energize these 2 solenoids and walk up to this and want to do a manual light off, you could do that by pulling this knob out, and you will have opened the valve, and you can manually light the valve. Also, if something bad happens and you have a fire of sorts, this very same knob can actually be recessed in. It takes a little bit of energy to push it in, and this mechanism here actually shut the valve off manually. So it has almost like an emergency shutdown in the field. So we have customers that use this mechanism in their upgrades, and following, as you saw in NFPA, it asks for a manual reset, and you saw where that applies. So a little bit of a summary. These are a couple customers on the list. Marathon, for example, looks at NFPA 85 and wants the fastest closing valves possible. Vista is also NFPA 85, and in-place leak testing. We can actually have our leak testing in place, as opposed to having to remove the valve and send out to a valve shop to be leak tested, which actually saves on downtime. We have Chevron on their Oasis project. They're doing the combination of doing a prescriptive standard NFPA 85 and then how safe the system should be per ISA 84, which is the same as IEC 61508. So this is kind of in summary, why one would pick these fast-acting, solenoids. A, speed of closure, all the certifications you can think of, fire safe, all the listings, UL, and so on, that get applied for maximizing and making sure you meet your standards and insurance needs for safe operation of your shutdown system. So that's where I'm going to stop, and we'll let Jeff open it up for Q&A.
All right. Thanks, Richard. We'll go ahead and open it up for questions at this point. Does anybody from the audience have any questions? Go ahead and unmute your phone, or go ahead and type it in. All right, we'll go ahead and wrap up today's session then. And if anybody does have questions that they want to email in, or any other questions in regards to the S8000 product from Maxon, or anything else that was discussed today, you can feel free to email me at jberger@loy-instrument.com, and we'll go ahead and field your questions. Thanks for your assistance today, Richard. It was a great presentation. We get a better appreciation for closing time on the valves and flame failure response time as well, and a lot of good information to share. So really appreciate all your help there, Richard. And thanks again, everybody, for attending. We will have another Tech Tuesday session, which is coming up 2 weeks from today. And we'll be discussing final control elements, final control devices, and how they apply to your process control system. So thanks again, everybody, for attending. And Richard, I'll give you a call here in a little bit, and go from there.
All right. Once again, thank you for the opportunity to talk to you and reach out to everyone out there, and have a great day. Thank you.
Thanks, Richard.
Appreciate it, Richard. Thanks.
Take care.